Hello, everyone. What I want to do now is finish up the slides on the basics of compound interest, part 2. And in particular, I want to talk about present value, and I want to talk about equations of value. Okay, so the concept of present value is extremely simple, and yet it is very, very important. So the concept is best illustrated through an example. Let's say I need $50,000 in 3 years. A 3-year CD offers an effective annual interest rate of 3%. So if you don't know what a CD is, it's a certificate of deposit. Certificate of deposit. So the basic idea there is if you put money in a certain bank account, and you keep that money in there for a certain number of years or a certain amount of time, in this example it's 3 years, then the bank will give you an interest rate that's generally better than it normally would. You're basically being rewarded for keeping your money in the bank for this 3 years or however long the CD lasts. Okay, so the question is, what amount do I invest in this account today to get $50,000 in 3 years? So I should say CDs really behave exactly like any other investment. The only, the only difference is in order to get this interest rate, you have to keep your money in the account for 3 years in this example. Okay, so how do we figure this out? Well, this is very easy. We know whatever I invest today is going to accrue 3 years of interest at 3% effective annual interest rate. So it's just A0, whatever it is, 1.03 cubed equals 50,000. That's how much I want in this account in 3 years. So you just take 50,000 over 1.03 cubed, and you get 45,757.08 cents. Okay. So if you understand this example, you understand the concept of present value. It really is that easy. Okay. And the terminology is present value, or PV for short, of 50,000 due in 3 years at 3% is 45,757.08 cents. Okay, and there's 2 ways to think about present value. One is that at this interest rate, 757.08 cents is worth 50,000 in 3 years. Okay, so in time, this 45,757.08 cents becomes worth more and more and more, which makes sense. If we had a dollar 100 years ago is worth now probably, I don't know exactly how much, but if I had to guess, maybe $10. I don't know exactly, but it's worth a lot more now than it was. Another way of thinking about this, and it's an equally correct way of thinking about this, is $50,000 was worth 45,757.08 cents 3 years ago. Okay, that's another way of thinking about it. Okay, so this illustrates the very, very, very important concept called the time value of money, which underlies everything we do in this course. Literally everything we do in this course. And the concept is money today is worth more in the future. Okay, the money that you have right now, is going to be worth more in the future. And I mean, technically speaking, that's not quite true. Money, like the US dollar, whatever currency kind of fluctuates up and down. But the idea is, and the reason why we state it like this, is that no matter what the situation is, there's always something you can invest your money in. It might be a bank account with an absolutely anemic interest rate. It might be a CD, a 3-year CD with a slightly better but still anemic interest rate. It might be a government bond that you're holding on to for 20 years. There's always somewhere you can put your money. There's always some way for money to grow in time. And when I say government bond, I mean particularly a U.S. government bond. So it's very safe. There's no chances of default, et cetera, et cetera. We'll get into that. We'll get into bonds actually later on. Okay. So generally speaking, money today is worth more in the future. Okay, and this is so important, what I'm going to say, that I'm putting it in full text here. And that is, and if you learn nothing from this course, if you just, drop this course after, you finish this lecture, but you learn and appreciate this concept, I'll be fairly happy because it's such an important, useful concept. And that is, whenever you make any business decision, any investment, any transaction, you have to take the time value of money into account. Okay? And the reason is any money, any business decision you make, any expense is money that could have been invested somewhere else. Okay? And again, by that I mean maybe you don't like the volatility, maybe you're worried about the stock market being in a bubble right now, which is a fair worry. You can still invest you can still put your money in a bank account or a CD or a bond, something safer. There's always somewhere you can put your money, and that has to be taken into account. Otherwise, you're just not making good business decisions. Okay, so the formula for present value is extremely easy. So apologies, there should be parentheses here. The present value of K dollars due in T years is K times nu to the T, where nu is this present value factor 1 over 1 plus I. Okay? And we basically have already used this formula. Here the present value factor is 1 over 1.03 cubed. And we said A0, just dividing by 1.03 cubed, A0 is $50,000 times 1 over 1.03 cubed. Okay, so we did implicitly use this formula to answer this problem. Okay. And this is called the present value factor. It's sometimes called the discount factor. And again, the meaning here, not to be redundant, but just to really drive home the point that, because it's so important, this here is exactly the amount we need to invest right now at an effective annual interest rate I to have K amount in T years. Okay. Again, I'll just, in this example, 45,757 is 45,757.08 is exactly the amount I need to invest right now into the CD to have $50,000 in 3 years if the effective annual interest rate of the CD is 3%. Okay, so let me do a very, very practical example. And this is exactly what you do in accounting, and you probably will do this in accounting courses. Let's say you have a $50,000 liability due in 10 years. Let's say the company, it's been a long day, sorry about that. The company can invest into some fund earning a 4% effective annual interest rate. Let's say it's a very safe investment. As an accountant, what you would do is say, well, really the current liability that you're going to write on your books is, in the terminology, is discounted by 10 years. And what do I mean by that? You're basically taking the present value of $50,000 due in 10 years, at 4% effective annual interest. You just plug into your formula. And what does this practically mean? And again, just exactly what we talked about a second ago. Right now, the company needs to invest $33,778.21 into this fund to have $50,000 in 10 years to pay off this liability. So it only makes sense then to say right now, really, the debt is $33,778.21. It doesn't really make sense to say right now my debt is $50,000 if it's owed in 10 years. Right. So, right. Or maybe in shorthand, another, like a quick way to say this is the current liability is the future liability discounted by 10 years. Okay. Now, obviously, this is subject to accountants and, playing games, thinking they can get, the company can get an unrealistic rate of return. They can invest in a fund, earning an unrealistic interest rate, but we're not going to get into that. Okay, so let's talk about equations of value. And in some sense, we'll spend a lot of time on this because basically a good chunk of this course, if not almost the entire course, is based on loans and loan type payments. Okay? So from that perspective, we're going to essentially kind of introduce loans early on. Loans and loan payments, particularly your student loans, your car payments, your mortgage if you have a house, they are equations of value. Okay? And what is an equation of value? It's deceptively simple. I say deceptively because, well, I can sum it up very quickly. It's very easy to describe in words. It's this time-valued sum of obligations equals the time-valued sum of payments received. Okay? But there is some subtlety in time-valued, and we'll do an example to illustrate that. When I say subtlety, you really have to do some work to actually get the time-valued sum of both of these. Okay? One thing I want to emphasize is that this is just how loans work. Okay? It's not my decision to make. I didn't decide that loans work this way. This is just the way loans work, and similar transactions like bonds and things like that. Okay. All right, so how do you find unknowns in equations of value? The easiest thing to do is pick a convenient reference time, and it's not that important to pick the best convenient reference time. If it's not clear what the most convenient reference time is, probably just pick at the end of the loan or at the very beginning of the loan. So you move terms before this forward in time to your reference point, and you move terms after this backwards to your reference point. Okay. Right, and if you picked your reference time to be the beginning of the loan, then you move everything back to the beginning of the loan. If you picked your reference time to be the end of the loan, you move. Sorry, I should say for B, if you I have to switch that up. My apologies. If you pick the end of the loan to be a reference time, you move everything forward to the end of the loan. And by move, I mean you value everything at the end of the loan. You take the time value of everything at the end of the loan. If you pick your reference time to be at the beginning of the loan, you move everything back. You take the time value of everything relative to the beginning of the loan. Okay. all this will be much more clear if you just draw a time diagram. So let me do an example to illustrate a lot of this kind of abstract wording. Okay, so every Friday in February, so the 7th, 14th, 21st, and 28th, a person places a $1,000 bet on credit. The betting service charges a weekly interest rate of 8%. I mean, this is, of course, unrealistic to some degree. This would be loan sharking and probably is very illegal, but that's all right. Just an example. Okay. Unfortunately, he loses each bet and agrees to pay his debt in 4 installments to be made March 7th, 14th, 21st, and 28th. The payments are $1,100, 7th, 14th, and 21st. How much does Walt have to pay to completely, on the 28th, to completely repay his debt? So the basic idea is very simple. Walt takes out a loan and he gets $1,000 on the 7th, 14th, and 21st, and he pays back this loan on the 7th, 14th, and 21st of March, and he makes finally an unknown payment on March 28th to completely repay his debt. All right. So let's look at this problem here. Okay. So, so right here we have, let me get my little pencil out here. So this is these are the payments here that he received. This is the money he received. And this is his obligations. This is what he has to pay, all 4 of these. Okay. All right. So, right, so here the unknown occurs on March 28th. So it only makes sense to make that our reference date. Okay? So we're time valuing everything here relative to March 28th. Okay, so what's the 3/28 value of payments received? Well, let's figure that out. Okay. So first of all, let's look at the value of the payments that, or the $1,000 that Walt got on February 7th. So that's right here. So that accrues, well, how many months of interest? 1, 2, 3, 4, 5, 6, 7. That accrues 7 months of interest. So the value, the time value of this $1,000 on March 28th is exactly what I have right here. It accrues 7 months of interest at 8% effective interest per month. So it's 1,001.8 to the 7th. Okay. We do the same thing for the February 14th payment. All right. What is the time value of that on March 28th? Okay. Well, that 1,000 accrues 1, 2, 3, 4, 5, 6 months of interest. The interest rate is 8% per month. So it's 1,001.08 to the 6th. And you do that for each of these 1,000 payments that Walt got. And if you do that, then the time value of these payments that he received on March 28th is $6,130 and roughly 52 cents. We do the exact same thing for the payments Walt has to make. Right? That's important to remember when you pay off a loan, that not only does your loan obligations accrue interest, but your loan payments accrue interest. And again, this is just the way loans work. It's not like you might be thinking this is kind of silly, this is kind of convoluted. I mean, it can't argue it is a bit convoluted, but this is just the way loans work. Okay. Okay, right, so we're going to do exactly the same thing. Let's take the first 1,100. How much is this 1,100 worth on March 28th? Well, same idea. It accrues 1, 2, 3 months of interest. So it's 1,100, 1.08 cubed. Do the same thing for everything else. And finally, at the end of the loan, on March 28th, Walt completely pays off the loan, and henceforth, that X payment does not accrue any interest. All right. So you add all this up, 3,856 and roughly 72 cents plus X. So the equation of value is you just add these two up. Because again, remember, what is an equation of value? It's the time value of payments received equals time value of obligations. Okay. And I should mention, theoretically, it doesn't matter what your reference time is. You're still going to get the same answer. It's just sometimes are convenient versus the others. And, for example, it was convenient to pick the end of March for our reference time because now, this payment of X, this last payment, doesn't accrue any interest, so there's nothing in front of it. Though, doesn't make life that much easier. It was just slightly more easier to pick the end of the loan as our reference date. All right, so you solve for X, and you get possibly a very surprisingly high number, $2,273.79. Okay. So from that perspective, let's just right. So without time value of anything, the total of the payments received, non-time valued, is $4,000. On the other hand, if you add all three of these up, well, you get something pretty much like $6,000, actually. Or maybe about more like 5,500. So in this example, you are paying $1,500 in interest. Right. Okay. So let's do a very similar example. Let's do the exact same example, except the 328 payment is 1,100, but the 314 payment is unknown. Okay. So now in this example, it's let me just go here. It's most convenient to pick my reference date again when the unknown occurs. Though if you really want to, you could still pick 328 as your reference date and time value everything relative to 328. Not only is it a little easier to pick 314, I think it's good practice to pick different reference dates and time value everything to that reference date. So let's do that. The concept is exactly the same. Okay. So let's look at this 1,000 here, and I'll only do that first 1,000. So how much is this $1,000 worth on March 14th relative to 8% interest? Well, it accrues 1, 2, 3, 4, 5 months of interest. So it's 1,001.08 to the fifth. And you continue on until you hit the last payment that Walt made, which is this 1,000, and that accrues 2 months of interest. So on March 14th, it's 1,001.8 squared. That's $5,255 and roughly 93 cents. Okay, So here's where things, I don't know if it gets tricky, but if you understand everything I've said, it should be pretty straightforward. So here we're going to move this one forward. Okay, so for the obligations, the 1100 accrues 1 month of interest. X, well, the value of X on March 14th is just X, because X is the obligation payment made on March 14th to the bookkeeper. Okay. On the other hand, we have to move this 1100 backwards in time. So what was 1100 due? How much is 1100 worth 1 month ago? Well, we take the present value of 1100 back on 3/14, or we discount it by 1 month. And we do the same thing here. We discount the 3/28 payment to the bookkeeper by 2 months. Okay. And so that becomes, first 1100 again accrues 1 month of interest, 1100, 1.08. The X doesn't accrue any interest. You don't discount it. It's made, the payment is made on the reference date. The 1100 is discounted by 1 month, so 1.08 to the -1. The 1100, the last payment is discounted by 2 months, so it's 1.08 to the -2. And it's $3,149 and roughly 49 cents plus X. And you solve, and you get an answer that's roughly the same. It's off by like $100, $26.34. Okay. So if you have any questions about this example, if anything I said is unclear, please, please, please email me, put up a YouTube comment, meet me in office hours on Zoom. Really, what I'm doing here, this is a very, very, very important example and really gets to the heart of this course, which is dealing with loans and loan type transactions. Okay. Okay, so let me introduce a very, very important formula that we'll use implicitly over and over and over and over again. And when we're done, we'll use it again. Okay, I exaggerate a little bit, but so I'm sure you're obviously in a math course. If you're a math major, you've seen this, but even, you should have seen this in an economics course. The multiplier effect of an investment, a government investment, things like that. This is the finite formula, the finite geometric sum formula. So if R is really any number not equal to 1, and n is a positive integer, then if I take 1 plus r squared and add up all the way to r to the n, that's going to be 1 minus r to the n plus 1 over 1 minus r. Right? So let's put this to use. And I want to do this example. It really gets to the heart of very practical business decisions that often have to be made. So let's say a machine costs $500,000 and has maintenance costs associated to it at $2,000 per month at the end of each month. And it lasts 3 years and can be sold for $50,000 at the end of 3 years after paying this last maintenance cost. Now let's assume that 5 people can do the work of the machine and workers are paid at the end of each month. If effective annual interest is 6.17%, and that's just to make the problem a little easier, when you do calculations, then find the most you can pay the employees if you want to hire employees rather than getting the machine. Okay. So how am I going to do this problem? Well, I'm going to basically set up a time equation of value, and that is at the end of 3 years, the time value of the cost of the machine is going to equal the time value of your employee expenses. Okay. And particularly, that'll tell me how much I can pay each employee per month. Because if I pay the employee any more than that amount, then the time value of employee costs is going to be more than the time value of the machine. And that's not really a good business decision to make because that's money you could be investing in this account at 6.17% effective annual. Okay. Right. And of course, this is, I mean, you know, there's taxes to think about. There's, you know, benefits to think about, you know, health insurance benefits, et cetera, et cetera. But this is just a simplified example to just illustrate how you really have to think, you know, to make good business decisions. And this is how corporations really do think. Okay. And again, every single cost has to be time valued. The logic being any expense that you make, any cost that you incur is money that could have been invested in your account earning 6.17 effective annual interest. Okay. All right, so let's get to the problem here. Okay, so first and foremost, I want to convert this interest rate, 6.17, into an equivalent monthly interest rate. So let's say J is the equivalent monthly interest rate. Okay. Sorry, that E got a little mangled. Okay, so what do I have? And I'll do this right here. Well, if I accrue, or if we compound monthly interest 12 times, then that's the same thing as compounding yearly interest. 1 plus 0.0617 to the 1. So compounding monthly interest 12 times is the same thing as compounding yearly interest once. That should be self-evident. Okay, so, right, so how do we solve for, that's a comma, not a J. So how do we solve for J? Well, first of all, I want to just make clear that's possibly a bit silly to have, sorry about that, I don't know why. There we go. It might be a bit silly to think about putting an exponent of 1, but I'm putting that there to emphasize that we're compounding yearly interest once. If this was a 2-year span, it would be a 2 here, and this would be 24 months. So with that perspective, let me just get rid of that. So we just take, well, solving for J, it's very straightforward. You just take 1.0617 to the 1/2 minus 1. And if you do this in a calculator, and this is why I picked 0.0617, we get this very nice monthly interest rate of 0.5%. Okay, so with that in mind, let me draw a time diagram of the machine costs. All right. So I initially, and here I'm actually thinking of costs. So we're just doing a time value or equation of value with costs. So here costs are going to be positive. Okay, so that means when I sell the machine, that's going to be negative. Okay, because it's kind of negative cost is profit, or rather negative cost is revenue. All right. So from that perspective, we have the 500,000 cost that we make at the very beginning. And then at the end of the first month, end of the second month, all the way to the end of the last month, which is the 36th month, 36 months and 3 years, we have to pay the $2,000 in maintenance costs. Okay? And we also get 50,000 back. Again, it's kind of cost, quote unquote, cost of minus 50,000, since costs are positive here. Okay, so let's do the time diagram for employee costs. Well, we pay employees at the end of each month. And let's say X is the monthly employee salary. There's 5 of them. So at the end of each month, we have to pay 5X. So that's pretty straightforward. Okay, so let's use this to get the actual machine costs. And so here there's really no super convenient reference time. Let's just make the reference time at the end of the 3 years. If you want, you can make it at the beginning of this whole 3-year period. That's not going to be much harder, if at all harder, but. So let's just make the reference time at the end of the 3 years. So we're going to play the same game. So to give me some room, let me get rid of all this stuff I had here. 1 second. There we go. Okay, so we play the same game here. We ask, well, 500,000. How much is that after 3 years relative to my interest rate, monthly interest rate of J equals 0.005, which is 0.5%. And sorry, by after 3 years, I mean after 36 months. Well, the 500,000 accrues 36 months of interest at interest rate 0.5%. So it's 500,000, 1.005 to the 36. Okay. What about the next $2,000? Well, that accrues 35 months of interest. So the value of 2,000 at the end of the 36 months is going to be 2,000, 1.005 to 35. And we keep doing this until we finally get to the very last we keep doing that until we get to the second to last $2,000 for maintenance cost. Okay. And so that occurs at the 35th month. So how much is that worth at the 36th month? Well, that just accrues 1 month of interest. So it's 2,000 times 1.005 to the power 1. Sorry about that. So that one is right here. Okay. What I just circled here is exactly how much this is worth. Sorry about that. At the end of the last month. And last but not least, we have the 48,000 here. There's 2,000 minus 50,000. That accrues no interest. So it's minus 48,000. Okay. Okay, so this is not really that bad. Yeah. So we have what I described gives me exactly what I have here. And I want to plug this into the finite geometric series formula. So nothing to do with, you just have to keep the minus 48,000. But what you do is, and you really have to keep the 500,000, 1.005 to 36. But we can basically, you know, slightly manipulate what I'm circling here and dump it into the finite geometric series formula. In particular, you factor out a 2000, you factor out a 1.005, okay, to get the following. Okay. So what I have circled is exactly equal to this right here. Okay, so they are exactly the same. They are equal. Okay, I'm just factoring out again the 2000, 1.005, and then it's 1.005 to the 34 plus 1.005 to 33, all the way to 1.005 to the power 1 plus 1. All right. So, yeah, the 500,000, 1.005 to 36, and the minus 48,000 comes along for the ride. Right. And so here I'm using the finite geometric series formula with R equal 1.005 and N equal 34. So this should be, sorry, it didn't come out too well. This should be 35. 34 plus 1 is 35. And if you dump this into a calculator, you will get 627, $12, and roughly 47 cents. Right. Do the same thing for employee costs. Here you only need to factor out a 5x. Here your R for the finite geometric series formula, finite geometric sum formula, your R is 1.005 and your N is 35. So, right, so it's 1 minus R to the power N over 1 minus R. And we get 196.68 roughly times X, right? So you set these two to be equal. Again, you know, we found the time value of employee costs and we found the time value of machines. Set them to be equal. We get X is $3,187.97. And to put this maybe in a clearer perspective, that turns out to be $38,255.69 per year. That's the most that really makes sense to pay these employees. And again, realistically, you absolutely have to take benefits into account. If you do offer, you know, retirement benefits and health insurance benefits. But this is just a simplified example to take to you know, drive home really the point. All right. So I do very much like these kinds of problems because they really are, in my opinion, quite realistic. Yeah, if this doesn't make sense, I'll give something like this for homework. If this doesn't make sense, please let me know. It's really important to for this course to be comfortable with this kind of example. Okay, so in the next video or two, I will finish up compound interest and we will dive into annuities and loans and things like that. Very systematically look at annuity and loan situations. Yeah, so, and I understand this video, we definitely did harder things than the previous two videos, but you know, if you understood this video, then I definitely think you're going to be clear sailing for the rest of the course. You know, this is the kind of stuff we're going to look at throughout this course. Okay, so long, take care, have a good weekend, and yeah, stay safe, and I'll see everyone later.